random variables, which in the preceding videos we discussed observations, and now since we understand probability spaces, we can look at random variables and talk about what a random variable is, what makes it random, where its probability and distributional properties come from. And it's important for this video that you remember what measurable functions are. That was discussed in Class 4. So if you don't remember or you haven't seen that video, you can click on this link to that video, or this link will take you to the entire playlist if you want to reference any of the previous videos. So here we have on the right an outcome space that is the real line, and an event set that is the sigma algebra of the real line, which we call the Borel sigma algebra, and that makes up a measure space. And on the left we have another measurable space with its outcome set and event set. And roughly speaking, x is a function from one outcome set to another, and here x is a function from S to R, the real line, and x is a measurable function if the inverse is a function from the event set of R to the event set of S, that is from B to A. What measure the measurable space takes on doesn't matter. The probability measure is what we have pictured here. So remember that the measure Px on the event set B yields elements from the event set A, regardless of whatever the measure on A is, or if there is one being specified. The function x, as described here, is called a random variable. The key to understanding the meaning of a random variable is to understand that its distribution is directly derived from the probabilities in the model. It is not necessarily the frequency of a variable across the outcome space, such as the population being sampled. So let's look at an example. Suppose you wish to randomly sample a person from this community, and suppose you have a sampling frame for the whole community and you decide to engage in equal probability data generating process. So the numbers 1, 2, and 3 listed on the people in this community indicate where the person lives. Ones live on the far west side, twos live in the middle, and threes live on the far east side. But since you're engaging in equal probability data generating process, none of that really matters now, but it will come into play later. So your sampling frame gives you access to everyone in the community. Thus, all the community members are potential outcomes of your data generating process. So we're going to represent the set of all community members as the outcome set omega. If your event set, the sigma algebra of omega, is the power set, then any and all possible samples you could get, you will be able to apply a measure. And to reflect equal probability sampling, you will assign a probability measure to the measurable space because you applied equal probability sampling. Each person, which is each unit set in the power set, has the probability measure of 1 over 15 because there are 15 people in total in the community. So the probability measure is 1 over n, or 1 over the number of total people. Notice that each block here in these graphs are of the same size, indicating that each person has the same probability of being sampled. Let's call the sigma algebra of omega A. So we have A here. So what is x? Let's say x is a measurement, not a measure, but a measurement of the size of the person's house, measured in square feet. So it provides an assignment of a number on the real number line. Therefore, x is a function from omega to the real number line. Now, if x follows the rules of a measurable function, that is, for the measurable space of the real line and its sigma algebra, let's call the sigma algebra B, if for all the sets in the sigma algebra of the real line, the inverse of the function x assigns a corresponding set in the sigma algebra A, then x is a random variable. It is a random variable measurable A, and A, remember, is the power set of all the people in the community. The probability associated with the random variable is the probability that the data generating process will produce any of the members of the outcome set, in other words, any members of the community, that has the measurement on the random variable that you're interested in. So the question is, what are you interested in? You want outcomes with the values for x that fall in the set B. Say, for example, what is the probability that the data generating process will produce a person with a house that is greater than 5,000 square feet? First, you find the people whose houses are that large. Then you get the probability associated with that set from the original space. That is, the probability of the random variable having a value greater than 5,000 is the probability of the data generating process obtaining someone in the set of people who have a value greater than 5,000. There are 15 people in this community. There are 5 people with houses that are greater than 5,000 square feet. So the probability measure on the set greater than 5,000 square feet in B, the event set of the real line, equals 5 out of 15, or 1/3. The key point here is that the probability measure of a random variable is a direct reflection of an underlying probability space. If the underlying probability space is used to model a different data generating process on the same population, we could get a different probability measure for x. Let's say that the threes in the community are 3 times easier to get than the ones, and the 2s are 2 times easier to get than the 1s. And this is because the 3s live on the east side and the 1s live on the west side, and the 2s are in the middle, and your office happens to be on the east side, and you only had enough money to hire your nephew to do the job of surveying, and he's too lazy to drive all the way out to the west side. So even though their names might come up with equal probability in your random name generator, part of your data generating process is your nephew going out there to get them, and he just won't go out to the west side. It's harder to get him to do it. So the 1s are really hard to get. The 2s are hard to get, but not as hard as the 1s, and the 3s are really easy to get. So this changes the probability. The probability of the 1s is 1 out of 24. The probabilities of the 2s is 2 out of 24. And the probabilities of 3s is 3 out of 24. So the probability measure on the set greater than 5,000 square feet in the sigma algebra B equals 11 out of 24. But you typically are going to take more than one measurement on your study subjects. Let's say we're taking 4 measurements. This would be a random vector if you start with a vector valued function from an outcome space S to the real value space with 4 dimensions, because there are 4 components of the vector. And there is a sigma algebra on the 4-dimensional real value space, and each set in the sigma algebra on the real value space can be identified with a set in A, the sigma algebra on S. Each component of a random vector is a random variable. Suppose we define a vector-valued function of S as weight, height, blood pressure, and pulse rate. For each person in the outcome set S, the random vector X assigns 4 values, one for each of the person's weight, height, blood pressure, and pulse rate. Individually, these 4 characteristics are functions of S that are also measurable functions and are therefore each random variables with ranges on the real line. The vector-valued function x is a random vector, with a range being a space defined by 4 dimensions. So the definition of a random vector is similar to that of a random variable, except we can allow for dependence across random variables in the random vector. By considering the marginal or conditional probabilities across the distribution of random variables in the random vector, we can consider the probability distributions for each component of the vector. And we can consider the relationships between the components of the random vector, for example, correlations or regression equations. Let's go further to define the full product space associated with a sample size of n. And let's say we have a random vector of m random variables for each observation. Then we get an n by m random matrix, and this matrix has n times m random variables. The rows of the matrix are random vectors representing possible measurements on characteristics of observations. The rows are observations, and the columns of the matrix are also random vectors. They represent possible measurements of a particular characteristic across observations, and the columns are variables. Now, here we have a data set in a rows by columns format. So let's consider what the data represent if our underlying probability space is modeling a data generating process by first discussing what the data are not. The columns are not random variables, and the data themselves are not random variables. So these are not a random variable. Rather, it is each individual blank cell in our table that is better thought of as representing a random variable, because the blank cell is rife with possibilities. The blank cell actually contains a distribution of possible values that, once the data generating process is engaged, will fill the blank cell with a single datum. But until the data generating process is actually engaged, the blank table with all of its blank cells represents a random matrix of observations and variables. And the random variables are the blank cells containing various distributions. When the blank cell is occupied with a datum, that datum is just a particular realization of the random variable based on the data generating process. Random variables of a data generating process are represented by the distribution of possible values that can fill a cell in a table, not the actual data value that ends up in the cell. For example, it doesn't make any sense to say the data are dependent. The data are dependent. How is it that one data point, say 7, is dependent on another data point, say 33? What does make sense, however, is to say that two random variables in our random matrix are dependent. If the distribution of possible values that could fill one cell is different across or based on the possible values that could fill another cell. Moreover, our differentiating data from the distribution of possible data provides some clarity about descriptive sample statistics and inference statistics. Descriptive sample statistics are mathematical descriptions of the data, the number you actually have. Inference statistics are estimates of parameters associated with the distribution of random variables, and by implication characterize the probability space modeling the data generating process. So to reiterate, the columns of the data are not the random variables. The data are not the random variables. Each individual cell of the table represents a random variable with some distribution of possible values that could fill it. And blank table represents a random matrix. The data in each cell is just a particular realization of the underlying random variable. An important consequence of understanding that each blank cell in the table represents a random variable is to note that once you run the data generating process, you only ever get one realization of data for a given random variable. You only ever put one number in a cell. If you collect blood pressure measurements on a random sample of 100 people, you have one realization for each of 100 different random variables. So let me say that again. If you collect blood pressure measurements on a random sample of 100 people, so that's one variable, blood pressure, and 100 observations that you're collecting data for. Once you've collected the data, you have one realization for each of 100 different random variables. But if you only have one data point for each random variable, how can you presume to have enough information to inform your research? Certainly, if each random variable has a wholly different distribution without common characteristics, then not only do you have individual random variables, but you also only have one data point to inform each of their distinct distributions, which is a great lack of information. Which, if you look at this random matrix, is the case here. Each random variable has a wholly different distribution. So if you look at blood pressure alone, for the first observation, you have this distribution. For the second observation, you have a distribution that's skewed differently. Here you have a normal looking distribution. Here you have a bimodal distribution. So this random matrix sort of represents having different distributions for each random variable. Now, look at this random matrix. Here you have the same distribution for blood pressure and for each of the different characteristics or variables. The key to accruing information is to have multiple random variables that have the same distributional characteristic. For example, if our sample of 100 people represents realizations of 100 random variables, each from an implementation of the same type of data generating process on the same population, then we have realizations from 100 random variables that each has the same distribution for blood pressure. In this case, the data all inform the same distribution, even though each datum is from a different random variable. It's important to notice the distinction between having only one realization per random variable and having multiple random variables and thereby multiple realizations that have the same distributional characteristic of interest. This notion is implicit in the classic manner in which the sample mean is shown in introductory statistics classes to be an unbiased estimator of a random variable's expected value. To press this point further, if we have an n by m random matrix, m measures on n observations, comprising by necessity n times m random variables. Without further knowledge, we cannot combine the resulting data to inform questions regarding underlying distributions. Why? Because without further knowledge, we simply have a single realization from each of n times m completely different distributions, not sharing any characteristics of interest. We need to presume, by virtue of design or reasonable assumption, that some random variables share common characteristics in their distributions to warrant combining their corresponding data to calculate the value of a statistic that informs our question. So when are random variables dependent? Are height, weight, blood pressure, and pulse independent? Suppose we have a random vector with m elements defined on this measure space here. Then we simply have m random variables, which are measurements on the elements of our outcome set S. Here we have 4 measurements associated with each individual, and these 4 measurements compose a 4-component random vector with the random variables height, weight, blood pressure, and pulse. To understand whether these random variables are independent or dependent requires tying them back to the independence and dependence of events in the sigma algebra A. Because everything we do with the random variables must tie back to the original probability space. So first note that each random variable generates a partition on the outcome space, which can be used to generate a sigma algebra. A partition of a set creates disjoint subsets of that set, that is, subsets that do not overlap, but the sum of all these subsets accounts for all of the elements in the set. The partition created by a random variable can be used to generate a sigma algebra that is contained in A, the event set. The sigma algebra generated by the random variable is called a sub-sigma algebra of A. So let's do an example. Say you have a population of these people. That population is the outcome set S, and this measure space represents a data generating process that samples from this population. So now say you have a random variable called gender, and this random variable assigns the value 1 for females and the value 0 for males. The inverse function of the random variable for the value 1 and for the value 0 are elements in the event set A and are subsets of the outcome set S. Everyone in the outcome set, everyone in this population, is either male or female. The sub-sigma algebra generated from the gender partition is equal to this here. You have the original set, which is the universe set. You have the empty set. You have the set of all females and the set of all males. Random variables defined on a measure space, such as the one depicted here, are independent if their corresponding sub-sigma algebras are independent. In other words, the events associated with one sigma algebra are each independent of the events of the other sigma algebra. Random variables defined on a measure space are independent if their corresponding sub-sigma algebras are independent. So, Class 6 in this video series is called Conditional Probability and Independence. We will have a little bit of a refresher on independence, but if you want to go into greater detail, then go back and look at that video. Now, here's a refresher. Let's say we have two random variables, x and y, and we're going to call the sub-sigma algebras generated by the partition of the outcome set based on x. We will call that sub-sigma algebra A. And the sub-sigma algebra generated by the partition of the outcome set based on y, we'll call that sub-sigma algebra B. The random variables x and y are independent if the probability of B conditional on A equals the probability of B. Similarly, they're independent if the probability of A conditional on B equals the probability of A. Also, if the probability of A and B, that is the intersection of A and B, equals the probability of A times the probability of B. Here we can see two random variables, age and gender, each with two outcomes. And you can see that the probability that age equals greater than 65 for the whole population, that's right here, this segment above the red line, is the probability of age equals greater than 65, and you can see that's 50% of the whole population. You can see also that is the same as the probability that age equals greater than 65 for only the male population. So here is the male population. It's on this side of the green line, and greater than 65 years is also about 50%, or exactly 50%, for the male population. So the probability of age greater than 65 given male is equal to the probability of age greater than 65 for the total. And these two random variables are therefore independent. The same is not true here. The probability of age greater than 65 for the population is very different than that for the males. For the population, the probability is 50%. Above this red line, it's still 50% for the population. But for males, for just males, age greater than 65 is much greater than 50%. So these two random variables are not independent in this scenario. So far we've talked about dependence within observations. Now the question is, when are random variables dependent across observations? And the answer is, random variables for independent observations are necessarily independent across observations. However, random variables for dependent observations may or may not be dependent across observations. So if you know that observations are independent, then you also know that the random variables are independent across observations. But if you know that observations are dependent, then you don't know. Then random variables may or may not be dependent across observations. And remember that the data generating process is what determines whether observations are dependent or independent. So in the previous video on Class 8 on observations and clustered sampling, we learned that a clustered sampling design gives us dependent observations. An example of such a design is to randomly sample physicians and then from each physician that is contacted randomly sample from their patient pool. So the observations within physicians are dependent. So we can consider this two-coordinate subspace representing two dependent observations, observation 1 and observation 2. This here is our measure space of interest. It's a product space. And we want to know whether random variables measured on the space are independent or dependent. So we will call W any element of the outcome space, and W contains two physician-patient pairs, one for observation 1 and the other for observation 2. So this is W, an element from the outcome set. And we can define two functions on the outcome set. One of the functions equals 1 if patient on observation 1 weighs less than 150 pounds, and the other function equals 1 if patient on observation 2 weighs less than 150 pounds. And let's say these two functions map to the measure space containing the real line in the Borel sigma algebra, and let's say they're also measurable A1 cross product A2. So that just comes from the measure space that we had before here. So these are measurable functions, therefore they are random variables, and we can consider their probabilities Px as determined by P. So this is a probability space here representing the distribution of the random variables associated with the underlying data generating process. If x1 and x2 are independent, then the probability of B2 given B1 equals the probability of B2. This is so for all the elements of the two Borel sigma algebras. Again, the independence of random variables derives from the independence of their associated subsigma algebras. This table shows that patients 1 and 4 have low weight, less than 150 pounds. That is, so that X equals 1. And patients 2, 3, 5, and 6 have higher weight, greater than 150 pounds, so that X equals 0. So here we go. Patient 1 has 95 pounds, patient 4 has 125 pounds. The rest of these are above 150. Patient 1 is equal to 1, patient 4 is equal to 1, and then the rest of them are equal to 0. So what happens if we condition on the case of x1 equals 1? In other words, if observation 1 yields a patient with low weight. It turns out that there are 6 possible outcomes for which x1 equals 1. That is 6 possible outcomes when for observation 1 you get a person with low weight. So if for observation 1 you end up getting a person with low weight, that means you either end up with Chelsea or Chinton. Now, if we are sampling with replacement, then these are the 6 possible outcomes for which x1 equals 1. So for observation 1, you either get Chelsea or Chinton, and then this is observation 2 with replacement. You get 6 possible outcomes. Remember that each outcome contains 2 physician and patient pairs, and we're conditioning on the first pair. So if you got Chelsea as a realization for observation 1, then you would select from Dr. Ornish for observation 2 for x2, and you could get Chelsea again, Nicholas, or Caroline. If you got Chinton as a realization for observation 1, then you would select from Dr. Esselstyn for x2, and you could get Chinton again, or Sophie, or Brian. And 1 out of 3 of these have a patient in the second observation with x2 equals 1. So it's really 2 out of 6, or 1/3. So you can look at it with this table here. This table also shows the 6 different possibilities. So you would have patient 1 or patient 4 for observation 1. And then here's observation 2. And you could get these 3 or these 3 for physician 2. And you would again have 1/3 chance of getting another patient with x equal to 1 for observation 2. Now let's condition on the case that x1 equals 0. Let's condition on the case that for observation 1 we obtain a patient with high weight. There are 12 possible outcomes if x1 equals 0, and here they are. And remember, we are sampling with replacement. So if you got Nicholas as the realization of observation 1, then you would select from Dr. Ornish for observation 2. You could get Chelsea, Nicholas again, or Caroline. If you got Caroline as a realization for observation 1, then you would also select from Dr. Ornish for x2. You could get Chelsea or Nicholas or Caroline again. And the pattern is the same for if you get Sophie or Brian to collect data on x1 for observation 1. Then you would select from Dr. Esselstyn for x2, and in either case you could get Chinton, Sophie, or Brian. This amounts to 12 possibilities. Now, what is the probability of getting x2 equals 1 for the second observation? Again, among the 12 possibilities, 1/3 of them have a patient in the second observation with x2 equal to 1. So you would have these 4 equal to 1. x2 would equal to 1. 4 out of the 12, that also gives you 1/3. Quickly, this also shows us that given if sampling to fill observation 1 yields x1 equal to 0, then there are 12 possibilities for filling observation 2, of which 4 yield x2 equal to 1. So again, we have 1 out of 3 of the 12 possible outcomes for observation 2 yield x2 equal to 1. Whether we condition on x1 equal to 1 or x1 equal to 0, under both conditions of x1, the probability of x2 remains the same, and therefore x1 and x2 are independent. On the other hand, let's quickly look at the scenario in which x1 and x2 are dependent. This table shows that for patients 1, 4, and 5, x equals 1, and for patients 2, 3, and 6, x equals 0. And we condition on the case of x1 equal to 1. Observation 1 produces a patient with low weight. Now there are 9 possible outcomes for which x1 equals 1. Here are those 9 possibilities. So if you got Chelsea as the realization for observation 1, then you would select from Dean Ornish. For x2, you could get Chelsea again, or Nicholas or Caroline. If you get Chinton or Sophie when sampling for observation 1, then you would select from Dr. Esselstyn. Sorry, these are different doctors, Dr. Oz or Dr. Chopra. So you would select from Dr. Oz if you got Chelsea, and Dr. Chopra if you got Chinton or Sophie. For x2, and in either case, if you got Chinton or Sophie, you would get Chinton, Sophie, or Brian. This gives you 9 possibilities, and 5 out of 9 of these have a patient in the second observation with x2 equal to 1. So 5 out of 9 of these have a patient in the second observation with x2 equal to 1. Here are the 9 possibilities, and 5 of these are filled with 1 for observation 2, so again you have 5/9. Now let's condition on x1 equal to 0. That is, observation 1 produces a patient with high weight. Again, there are 9 possible outcomes. Here they are. But this time, there are 4 out of 9 for which x2 equal 1 in the second observation. Here we see the 9 possibilities, and the 4 that in the second observation would have x2 equal to 1. You have 1, 2, 3, 4. So, when we condition on x1 equal to 1, then we get that 5 out of 9 possibilities of x2 equals 1. But when we condition on x1 equal to 0, then we get 4 out of 9 possibilities of x2 equal to 1. So under the 2 different conditions of x1, the probability of x2 changes, and therefore x1 and x2 are dependent. So I want to thank you and advise you to run around being happy. Also, if you liked this, you can like it, subscribe, and comment. Thank you.